Start again. So, good evening, everyone. So, in this session, we try to understand the pin photodiode. So, actually, the problem in the previous PN diode is that actually the problem in previous diode. So, let's discuss what is the problem. Okay. First of all, so actually in PN junction diode. Okay. Am I visible? Okay. Let's see. So, what is the we are covering the topic PN or pin diode. Okay, so what is this? So semiconductor photodiode without internal gain. So what do you mean by without internal gain? So without internal gain mean that there is a no multiplication of the output. Okay, so see what of this, let me explain from scratch. So we are discussing the semiconductor conductor photodiode. Okay, photodiode without internal gain. Okay, internal gain. Okay, so what do you mean by this one? So photodiode without internal gain generate only one electron hole pair per absorbed photon. There is no multiplication. There is no multiplication of carrier, unlike avalanche photodiode. So we have to study three type of photodiode. One is PN junction. Okay, after that, there is some drawbacks and some limitation in PN junction. After that, we move for the PIN junction diode. Okay. Then after we move forward for the avalanche diode. Okay. So in avalanche diode we have to use the external gain. Okay, internal gain. Okay. So in pin junction diode, so there is a structure like the structure of diffusion and depletion. So let's see the structure of pin diode. So PN junction diode. There is PN junction and it operating in reverse bias condition. So what do you mean by reverse bias condition? In reverse bias condition, let's see. In reverse bias condition, the negative potential is applied to P side and positive potential is applied to the N side. Okay, and an immobile positive donor is present in the N region and immobile negative acceptor in the P region. Okay, free carrier electron are swept away. So free carrier electron and hole pair are the swept away, and the region become and this region become a depletion region. Okay, this region become a depletion region, and this region become a depletion region where the strong electric field is established due to the movement of electron and hole pair. This create a depletion region, and there's the strong electric field region inside the depletion region. Okay, and then after we see the diffusion region. Diffusion region is a region where lightly doped neutral area outside, simply we can say that the area outside the depletion region neutral. Okay, neutral lightly doped, a zero electric field. Simply there is no strong electric, but simply we can say zero electric field. Okay, carrier move by the diffusion. So all these the carriers, okay, electron will move by diffusion. Okay, so first of all we have to make the PN junction diagram. Okay, okay, PN junction diagram. Then after we have to make a electric field xy like this. Okay, in which we saw the electric field strength, and in depletion region we have to see the strong electric field. In diffusion and there is no electric field. Okay, The key point is that depletion width decreases. So depletion width increases with doping decreases. So as the doping things decreases, the depletion width increases. Okay, and we see, so absorption in the depletion is there. So one of the important point we have to remember that the absorption in depletion region best condition in depletion region electron hole pair immediately separated by the electric field in fast response having the high efficiency. Okay, absorption in the diffusion region, the electron hole pair outside the depletion region and hole must diffuse toward the depletion region. Okay, the holes move toward the depletion region. Okay, the conclusion, it is desirable that the maximum absorption occur inside depletion region. So maximum absorption of the photon occur in the depletion region. Okay, and we also depend on the material dependency. Okay, so higher wavelength penetrate the deeper larger absorption region. So if having any photon having the higher wavelength, so it absorb deeper. Okay, and that absorption region is far greater than silicon. So germanium depletion region is greater than silicon. Okay, then we have to study what so we see the vi characteristic. So vi characteristic of the pn, typically pn photodiode output characteristic graph is that in the current is given in this section, this axis, and the reverse bias voltage is given in this axis. We see that linear what do you say, the output characteristic of the reverse bias PN diode is that at at zero light at zero light at very low light the reverse leakage occur. Okay, reverse leakage current occur as the light increases. Okay, as the light increases the photo current increases linearly. So as the light increases the current also increases. Okay, we are seeing as the light current increases the photo current also increases. The photo current is almost independent of the applied voltage. The photo current, this one, the current is totally independent of the applied voltage. So we have to make for the high light level there is a high current produced. At low light level in dark region simply a low current is induced. Okay, this is the vi characteristic of the photo pn photodiode. Okay, then we move forward for the that we see the depletion region width and device performance, and we also have discussed the depletion region width and the we have to know. So to increase, as we know that the optical detector having the best optical detector having the high sensitivity. So as the depletion, to increase the sensitivity, the depletion region should be longer. Okay, the depletion region should be longer to absorb more photon. Okay, to increase the sensitivity. So how we increase the sensitivity? We have to increase the depletion region. So increase the depletion region, and which absorb the more photons. Okay, which absorb the more photons. Okay, to increase the speed and to increase the speed. Okay? Depletion region must be shorter. So depletion region must be shorter. Okay, so it reduce the drift time. That's why the depletion region is shorter. But if we for increasing the sensitivity, then diode has to trade off between these two things. Okay, to optimize the device performance. So that's why the PN diode were developed. So that's why PN diode is developed. Okay, PN sensitivity increase, but the speed is reduced. Okay, but if we decrease the depletion width, sensitivity decreases, but speed increases. So we have to compromise one of the properties that make the detector very good. So to overcome this problem, we have to use pin diode, pin photodiode. Okay, so in which we widen the depletion region and isn't the depletion region. Okay, as the depletion region is increased, the photo and the absorption also increases, and we can trade off between the sensitivity and the speed. So let's move forward for the next photo pin diode. So let's see. So pin diode. So here is the diagram for the pin diode. So the pin diode is an improved version of the PN diode. Okay. So pin photodiode, pin photodiode is the improved version of. We don't write, simply you understand. So actually the definition of pin diode we have to start. The pin diode is the improved version of PN diode designed to achieve the wider depletion region, higher quantum efficiency, higher speed, better performance as a long wavelength. Okay, it is the most widely used photodiode type in the optical communication system. So let's see. So what is pin diode? Pin photodiode is an improved version of PN diode. Okay, diode. And why? Because it designed to achieve because it is designed to achieve what? First one, wider wider depletion region. Okay, as the depletion region wider and more absorption happen, the sensitivity increases, but little bit speed get reduced, and higher quantum efficiency. Okay, quantum efficiency, high speed. Okay, high speed, and the better performance at long wavelength. Okay, the main goal of the pin diode mentioned here. Okay, so why pin diode structure is needed? Why there is a need of pin diode? So at the long wavelength, like 1.3 micrometer and this one, the photon penetrate deeper inside the semiconductor material. Okay, a wider depletion region is needed to absorb. As a wider depletion region is needed to absorb them effectively. In normal PN diode, widening the depletion region is limiting by doping level. Okay, so the second question is why pin pin structure is needed. Okay, why pin structure is needed? Because as we know in pinning, as we see in PN junction diode, and there is a depletion region. Okay, this is the depletion region. Okay, so when we say that at long wavelength like 1.35 micrometer, at 1.3 micrometer, the photon penetrate into the semiconductor material. So widening the depletion region is needed. So we have to absorb more photons. We have to widen the depletion region like this. Okay, we have to widen the depletion region like this. As we increase the depletion region, the device become more sensitive. And speed get reduced. Okay, but it is limited by the doping level. Okay, to overcome this problem, we have to introduce a new. So the solution for this is make a n region extremely lightly doped and almost intrinsic. So we have to make a, a new PNSL in which we have to make n lightly doped, extremely low. So we have to make a n junction, n side lightly doped. Okay. The structure of pin diode. The structure of the pin diode. So P layer. First of all, we see the P layer. Okay. So we see the P layer, then I layer, okay, and then after the N layer, okay. So P layer is the intrinsic or very lightly doped layer. So this is actually, if we compare from the previous PN junction, it is similar one, okay, similar one. This is P region, this is N region, but this region is very lightly doped. So this region is very lightly doped as compared to the edge of the N. So this region is separated and the name as I, okay, name as I. So these are very lightly doped region, main depletion region and absorption region, okay. N plus region is the highly doped for the good ohmic contact. To make a ohmic contact, we have to highly dope this region, okay. P I is the intrinsic layer, where intrinsic layer and very lightly doped as compared to N or P, okay. So key point, the entire intrinsic region is fully depleted. So the key point is that this entire intrinsic region is fully depleted region. So the absorption of the light and carrier drift occur efficiently, okay. So this region is very lightly doped, and this is intrinsic and fully depleted region. So fully depleted region in which the absorption occur efficiently, okay, as compared to this one. At the absorption increases efficiently, then the sensitivity increase, the speed increase, and the device become more efficient, okay. So as we see the electric field graph, so in P region little bit starting, but in the intrinsic region we see the strong electric field in the depletion and absorption layer, and there is a negligible or no strong electric field in the N region, where it's a highly doped region, okay. So PN diode showing the combined absorption. So PN diode showing the combined absorption and depletion region. So in this one we see that the combined absorption and the depletion region, okay. So let's see the operation of pin diode. So light enter. So let's see the operation of pin diode. So what is the operation of the pin diode? So as the light enter, light enter and it absorb in the wide intrinsic region. Okay. So as light enter, it absorb wide intrinsic region. Photon create an electron hole pair. Okay. Reverse bias condition, electron in the n side and the holes in the p side. Okay. Because the I region is wide and the field is uniform, the carrier drifts quickly. So as the I region is wide, there we see the I region is very wide, okay, and the field is uniform. As we know, the field is uniform in this region, okay. So carrier drift quickly. As a result, high speed and high quantum efficiencies. That's why there we observe the high speed plus high quantum efficiency, okay. This is the operation of the pin diode. As the light enter, okay. As the light enter, hole pair, reverse bias condition, electron in the n side, hole in the p side, okay. Because the I region is wide and any uniform field, this result in the high speed plus high quantum efficiency, okay. We have to see the silicon pin photodiode in the shorter wavelength. We have to see the silicon p diode for the shorter wavelength, okay. So and for the shorter length, so as the seven, this one. So in figure 8.7, we can say that the front illuminated pin diode, okay. So P here, I here, and N here, okay. So light enter from the top P side require a depletion width of 20 to 50 micrometer, okay. To achieve the 85% quantum efficiency, response time less than 1 meter, and the dark current approx 1 nanoampere. We use 0.8 to 0.9 0.8 to 0.9 micrometer operation. Okay. For the side illuminated pin diode, for the top view, these are the condition. Okay, for the silicon. And for the side view, the light enter parallelly from the junction side. So light enter from the junction side, and the very large absorption, because width of approx this width is approx 500 micrometer. So extremely effective near cutoff wavelength is 1.09. Okay, but in germanium pin diode. So this is the silicon pin diode. Okay, and now we have to discuss the germanium pin diode. Germanium pin diode. So it cover entire 0.8 to 1.6 micrometer range. Okay, but have a dark current because germanium has a small band gap. Okay, germanium has a small band gap and approx 100 nanometer at okay and nanoampere at 20 degree and 1 megabyte this one. Okay, and we have to see the indium gallium arsenide pin diode for a very for a long wavelength detector. For a very long wavelength detector, we use gallium arsenide pin diode. Okay, mostly avoid in a modern telecom system favored because it detects up to 6.7 micro ampere wavelength things. Okay, the structure we can see that if we axial layer of n plus, if it axial layer of the n plus region. Okay, n plus region, light absorbed in a low doped light is absorbed in the low doped intrinsic layer and energy band diagram shown in the homojunction. Energy band diagram show a homojunction between the indium phosphate or indium gallium arsenide. Okay, this was the structure for the indium gallium arsenide pin diode. So we can see this. This is the contact region. This is N region. Okay, so this one is a P region. Okay, and all this region are the N region. Okay, but this upper region is lightly doped as compared to this one. So as we can set a homojunction between this one. So P of if we start from this one, so P plus P side of indium gallium arsenide, then we move for the lightly doped region of the indium gallium arsenide and the highly doped region of the N side. Okay, okay. Add INP buffer. So performance is approx. Let's see the performance of this pin diode is the quantum efficiency is 75% to 100%. The dark current is less than 1 nanoampere. Okay. Depletion layer is approx 3 nanometer and the transmit time slot is 15 gigahertz. So this one is the advanced. So this is the advanced structure. This is advanced structure of pin diode. So in pin diode we see the definition. So in pin diode we see the definition why we need pin diode and through pin diode how we achieve this condition: wider depletion region, high quantum efficiency, high speed, and better performance for the longer wavelength. So why we use pin diode? Because there is some limitation in the PN junction diode. Okay. After that, we move forward for the after that we see the structure of pin diode PIN and distribution of electric field. Okay. Then we see the silicon based pin diode. Okay. Metal contact, silicon, depletion region, and the N region. So this is lightly doped region. This is highly doped region. Okay. This is a top view. This is a side view. Okay. Then we move forward for the indium gallium arsenide pin diode for the why we use for long wavelength detector. So we use metal contact we all use N region, but this one is a highly doped. N plus one is highly doped. Okay. Okay. So the summary of pin diode is pin diode include a wide intrinsic region, improved absorption and speed. Absorption occur entirely inside the depletion region, high quantum efficiency and fast operation. Silicon pin diode is a 20 to 50 micrometer depletion width and faster and giving the quantum efficiency of 85%. Okay. This give a quantum efficiency of 85%, and germanium pin diode has a span of 0.6 micrometer but having the dark current. And indium gallium arsenide pin diode are preferred for the long wavelength having 1.3 to 1.55 micrometer the fiber system. And okay, let's move forward for the this is advanced and this advanced pin diode, the structure like mushroom. So we don't need to study this topic. Okay, these are the speed and responsive things, so no need to study. So let's jump to a new topic, that is avalanche avalanche photodiode. So avalanche photodiode. Avalanche photodiode. So okay, let's see. So so semiconductor photodiode with we studied earlier without internal gain. Now we have to study a semiconductor photodiode with the internal gain. Okay. So there is a Blanche photodiode. Okay. So these photodiodes produce more than one electron. In previous semiconductor, we can see that it produce only one electron hole pair. Okay. There is no multiplication of the internal energy. Okay. So in these photodiodes produce more than one electron hole pair per absorbed photon because they use the internal multiplication mechanism. There is no internal multiplication mechanism in the semiconductor photodiode without the internal gain. Okay. The most important device in this category is avalanche photodiode. Okay, so we can say at APD. Okay, avalanche photodiode. So avalanche photodiode. So this one. So APD. So these are photo detector. So avalanche photo detector that provide internal gain. Okay, that provide the internal gain. Okay, that provide the internal gain through through the impact ionization. Through impact ionization. Okay, and this make it more sensitive than a pin diode, and this make it for more sensitive than the pin diode. Okay, pin photodiode. Okay, so we see PN junction diode, PIN PIN junction diode, and then we move forward for the new one is avalanche photodiode. So avalanche photodiode has a unique feature of internal gain through what impact ionization. This make a more sensitive than the pin diode. So sensitivity is directly proportional to the best detector. So it's more sensitive device, best detector. Okay. So let's discuss the structure of pin diode. Okay. Sorry, avalanche diode. So structure of the avalanche diode. So an absorption or depletion region, silver, where photon generate carrier pair. So in avalanche diode, we can see N P I P. Okay, this type of region. Okay, an absorption has In absorption layer where the photon generates its carrier pair. Okay, in absorption layer there where photon generate the carrier pair, and very high electric field region where carrier multiply. So we can see the very high electric field in this region. Okay, after that it decreases gradually. Okay, and the electric field is approx 3 into 10 power 5 10 power 5 volt per meter. So this is a very high accelerator carrier to variation. The principle of the operation that is impact ionization. So in avalanche, diode when the photon is absorbed. So let's see, when the photon is absorbed and the electron hole pair is generated. Okay, but inside the high electric field, the carrier gain enough kinetic energy to create an additional EH pair by the collision. Okay, and so the question and the explanation is that the basic principle that the basic principle that impact ionization. So ionization. So when when a photon absorbs the electron and hole pair, it generated in when a photon is absorbed and electron hole pair is generated inside the very high electric field. Inside the very high electric field, the carrier get a very high speed and high kinetic energy, which create an additional electron hole pair by the collision. Okay, so electron hole pair gain high kinetic energy and collide with another one and produce another electron hole pair. Okay, so this is the impact of ionization. So this process is known as the impact ionization. Okay, as the carrier move, one electron can create several this electron and hole pair. We can denote as electron hole pair like this. Okay, after after coming inside the high electric field, it move faster and collide with another electron hole pair, and which generates the another electron hole pair. Okay, so there is a multiplication of the electron hole pair. Okay, as the carrier move, so electron hole pair is termed as a carrier. So electron hole pair, one electron can create several more, and these new carrier create also more carriers. Okay, this lead to an avalanche. So the technical meaning of avalanche means exponential multiplication of carrier. Okay, avalanche means exponential multiplication of carriers. Okay, result in the internal gain. So APD avalanches photodiode typically achieve multiple factor. Okay, typically get a multiple factor. So term as a M. Okay, approx 10 from range from 10 power 2 So reverse bias requirement. So avalanche photodiode must be reverse biased at high voltage to create a high electric field. Okay. So photodiode must be in the reverse biased at high at high voltage. Okay. To create the high electric field. And typically the biasing voltage approx 50 to 50 to 400 volt. Okay. And the newer APD operate as newly avalanche photodiode operate at the 15 to 25 volt. The operating is too close to the background and excessive noise. So it and the operating voltage is too close to break down the excessive noise, and that bias must be controlled precisely. The problem that limits again, even though the theoretically the even though theoretically a very high gain approx m is equal to 10 to the power 4 possible, in practical microplasm like a small defective region with the lower breakdown voltage created cause the uncontrolled local breakdown must be avoided using the high quality material to precise. So there is some internal inside this one. The small defective region is created due to the high breakdown voltage. This can be controlled using high quality of material. Okay. Age leakage. Age leakage things happen into the APSD. So how can we solve? So we can solve by using a guard ring. We can see that a lancet diode. So there must be a age leakage things happen in this region. Okay, we can see that the age leakage things happen in this region. To avoid this, we have to use so a guard ring like this inside the outside the lancet diode. Okay, use a guard like things. Okay. Material used for the APLA launcher diode is silicon, silicon, EPDs, and German APDs, and indium gallium arsenide. Okay. To achieve the high speed performance, the EPD must be fully depleted in absorption region. Okay. And if the carrier are generated in undepleted region, they diffuse slowly and long diffusion tail. Okay, slow down the response and decrease the high speed performance. Thus, the strong high field is needed to make all carrier drift at a saturation voltage. So, how high speed operation is required? So, to achieve the high speed performance, the APD, so avalanche photodiode must be in depletion region absorption. Okay, if the carrier generate if carrier generator if anything generated in this region, okay, it's like a P region. Okay, so this lead to be a diffusion and this slow down the performance. Okay, so that's why we need high field. That's why we need high field. Okay, so factor limiting the APD responses are transmit time, avalanche build up time, RC time. So we have to skip this topic. So summary in short, we have to explain the APD, that is avalanche photodiode, provide the internal gain through the impact ionization. You understand the impact ionization by saying this: when a carrier carrier moves in the high electric field, it gain the high kinetic energy and produce another carrier. Okay, this is a multiplication of things happen. Okay, in high electric field. So avalanche photodiode provide the internal gain through the impact ionization in the high field region, and the gain is ranging from the 10 to the power 2 to 10 to the power 4. Okay, but depend on the device quality also. Okay, the problem like microplasm or age leakage, we use guard ring as we select. If any age leakage or microplasm thing happen, we have to use the guard ring. Okay, and speed limited by the transit time. So if excess speed is crossing, so we have to use transmit time and avalanche build-up time. Okay, so APD has a constant gain bandwidth product. The output pulse are the asymmetric. Okay, and material we use is arsenic, gallium, or indium gallium arsenide. Okay, so we covered the detector topic. Let's summarize all the things. So there is no need silicon.